The doubling period of a bacterial population is 10 minutes. At time t equals 100 minutes, the bacterial population was 60,000. So did you catch that? The doubling period for the bacterial population is 10 minutes. That means every 10 minutes, the population of the bacteria doubles. At 100 minutes, it was 60,000. What was the initial population at time 0? And find the size of the bacterial population after 5 hours. Okay, so this is doubling. So whenever, when a population multiplies or divides by the same number every same period of time, I should say. Every same period of time, that is exponential. Exponential growth if it's multiplying, or decay if it's shrinking because it's dividing. And that means you use the formula y, you could use a, it doesn't really matter, but y equals a times b to the t. That's the formula we use for population multiplying or dividing every same period of time. So in other words, they're saying it's doubling every 10 minutes. So that's multiplying by 2 every 10 minutes. That's exponential growth. That makes it explode, right? If the population's going to double every 10 minutes, it's going to grow super, super, super fast. And that's as opposed to, what if the population was just going up by, I don't know, 1,000 bacteria. The population was going up by 1,000 bacteria every day, or even every 10 minutes. So up by 1,000. Now that's adding. That's not doubling. That's adding 1,000. So that would be y equals mx plus b. That would be linear growth, not exponential. Do you see the difference? So if it's just adding the same number, or even subtracting, like a car depreciates, goes down in value by $1,000 every year, that's linear. That's y equals mx plus b. That's just linear. The x is just on the base level. If you're just adding the same number every period of time, every 10 minutes or every year or whatever, or if you're subtracting the same number, just adding or subtracting is linear growth. It's adding or subtracting the same number. Adding or subtracting the same number. That's just linear growth. But if you're multiplying or dividing the same number, that's more powerful. That's exponential growth or decay. And in that case, you see the t is in power. Let me do a little better job on that. The t, the time, the letter, is in power. He's up in the power zone. He's not just on the base level like the x is here. Doesn't matter whether you call it x or t, whatever, it's just the variable. But is it on the base level? Like for linear growth, that's more tame, that's slower growth. If you're just adding the same number or subtracting the same number every period of time. If you're multiplying or dividing the same number every period of time, then the t gets up in the power zone, exponent zone. That's exponential growth and decay. All right, so we're doubling, and now when you have the doubling, that's the 2, so that makes the base be 2, and the time it'll be t over the doubling time. T over the doubling time. So this will become a times 2 to the t over. Now what's the doubling time? How long does it take to double? It doubles every 10 minutes, right? T over 10. Do you see that? You put the doubling time down there. So that's how we set up the formulas for a doubling problem. You make the base 2 and you put the t over 10. Do you see how that works? I don't want that to be magic. Look at that logically. What does that mean? That means 10 minutes later, the population will double, right? So if I put in 10 for t, this will be t to the 10 over 10. In other words, that'll be 1. So in other words, it's a times 2. It's 2a. See how the population doubled? In 10 minutes, when you plugged in 10 for t, 10 over 10 made that 1. 2 to the 1 is 2. That has a doubling effect. Whereas if you make t 20, 20 minutes later, it'll double twice, won't it, right? Every 10 minutes it doubles. So in 20 minutes, it would double twice. So this would be y equals a times 2 to the 20 over 10. That's 2 to the 2. 20 divided by 10 is 2. 2 squared is 4. This is 4a. It's quadrupled. It's doubled twice. It's times 4. See how that's working? See how putting t over 10 is the way to go? You put the t over the doubling time, and that makes it actually work. Let me get rid of all this side scribble stuff. So here, make that t over 10. So t over 10. So that's how we do it. We always put the t over the doubling time, and that'll make it double every period of time that they've told us it should double. Okay, so that's our basic formula. We're going to always work with that on a doubling problem. Let's go forward now. Now, the first thing we're going to need to do is take the first information they gave us. They told us that at 100 minutes, the population was 60,000. So let's plug in right here. 100 minutes, the population became 60,000. At 100 minutes, the population became 60,000. So 60,000 at 100 minutes. When time is 100, the y, which is the population, becomes 60,000. Now, solve for a. A, by the way, is always the starting amount, the starting population. So whenever we use these formulas, y equals ab to the t, the a is always the starting population, and that's what they're asking for. That's their first question. What was the initial or starting population at time 0? Do you see how that's going to be the case? Well, let's go on and solve it. So this will be 60,000 is a, to 100 divided by 10 is just 10. So now to solve that equation, divide, well, here, why don't we first figure out what that is? On our calculator, this will be 60,000 a. 2 to the 10th, I believe, is 1,024. If you use your calculator, raise 2 to the 10th power, get 1,024. Now divide both sides by 1,024, and a will equal, let's see, 60, 1, 2, 3, divided by 1,024 on our calculators. So a is coming out 58.59375. Kind of running out of room there. 59375. Okay, so we got A. That's the answer to part 1. They want us to get A. And now we can go on with part 2. Part 2 now, we can again write the formula that we've got here. Y equals A times 2 to the t over 10. But now we know A. Now we know A. So we can say, okay, this formula is 58.59375 times 2 to the t over 10. Okay, so, oh, by the way, do you see why, when you have the formula y equals a times b to the t, do you see how a is the starting amount? I want to make sure that's clear. Starting amount when t is 0. So meaning if you plug in 0 there for t, you get y equals a times b to the 0. And anything to the 0 power is 1. So y will just be a. Do you see how the y will just be a when you plug in 0 for t? So at time 0, at the start, the y value is just a. That's why we say that the a in the front is the starting population. That a is the starting population. All right, so now we're ready to answer the second question, which is they say right here, find the size of the bacteria population after 5 hours. 5 hours. So we need to do that. So after 5 hours, I should make t be 5. Is that right? There's a small mistake I'm making. What's my mistake? What's t? In what kind of units is t? What have we been using all along? What kind of time units have we been using? What is this and what is this? Minutes. We've been doing everything in minutes. You cannot change the time units. Whatever you do, you can do it all in time, all in minutes, all in hours, all in days. You can do whatever time unit you want. There's no limitation. Seconds, weeks, whatever you want, but you have to be consistent. You can't change halfway through. So if we started with minutes in the beginning, we got to keep going with minutes. So I got to take that 5 hours and change it to minutes. So 5 hours is 5 times 60 minutes. So you know that's 300 minutes, right? 5 hours is 300 minutes. So that's what I have to do. I have to plug in 300 minutes to the formula. 58.59375 to the 300 over 10. So I plug in 300 for t, and that's going to be 58.59375 to the 30, right? If you divide 300 by 10 on your calculator, you get 30. And so put this in your calculator. I'm getting here's what my calculator just told me. It told me 6.291456 E10. Did you get that? E10. Now what is that E10? This means times 10 to the 10th power. That 10 is the power of a 10, which means it's scientific notation. It's the way your calculator is telling you exponent. The E stands for exponent 10. It's telling you the exponent, the power on a 10 should be 10. Means move the decimal right 10 places. Move the decimal to the right 10 places. So 6.291456. So I should take that decimal, which is right here. It doesn't really belong there. It goes right 10 places. Remember, when you multiply by 10, that moves the decimal one spot, right? If you multiply any number by 10. So multiplying by 10 to the 10th, that's multiplying by 10 10 times, that moves the decimal 10 places to the right. That's what your calculator is telling you with this E10, that the decimal doesn't really go here. It's just putting it there for a moment. It goes 10 to the right. 1, 2, 3, 4, 5, 6. 6, and I'm to the edge of the number 7, 8, 9, 10. 7, 8, 9, 10. So the first 6 jumps take me to the edge of the number. The other 4 go beyond the edge, so they bring in zeros. So there's the actual population, 6.291.456.0000. What is that? Let me see, comma. That's a crazy big number. This is million, so this is billion. That's 62,914,560,000. That's the population that for the bacteria after 5 hours. That population is exploding. That's almost 63 billion. And that's just 5 hours later. Do you see how that bacteria, that exponential growth is explosive growth? It just, remember, it started at what? It just started, what was the initial amount? 58? right? Around 58. You can't have 58 and a half bacteria, but it means approximately 58 bacteria started, and then it doubled every 10 minutes, and 5 hours, was it? Yeah, 5 hours later, it's at 63 billion bacteria. That's crazy. That's the power of exponential growth.